Once again, let's look at the 2008 swing state data on the county level. We'll think about other summary statistics we can calculate. In this B-swarm plot, I also show the sample means of each state with a horizontal line. In looking at this plot, the mean seems to capture the magnitude of the data, but what about the variability, or the spread of the data? Florida seems to have more county-to-county variability than Pennsylvania or Ohio. We can quantify this spread with the variance. The variance is the average of the squared distance from the mean. Whew, that definition was a mouthful. Let's parse that more carefully with a graphical example, looking specifically at Florida. For each data point, we square the distance from the mean, and then take the average of all of these values. Calculation of the variance is implemented in the np.var function. Now, because the calculation of the variance involves squared quantities, it does not have the same units of what we have measured, in this case the vote share for Obama. Therefore, we are interested in the square root of the variance, which is called the standard deviation. This is calculated with the np.std function, and the results are the same as taking the square root of the variance. When we look at the swarm plot, it is clear that the standard deviation is a reasonable metric for the typical spread of the data. Okay, let's practice computing some variances and standard deviations. We have more data than just the vote share for Obama. We also know the total number of votes for each county. Let's look at how these two quantities vary together. We start by looking at a scatter plot of the county data for the three swing states, plotting the percent vote for Obama versus the total number of votes in each county. Immediately from the scatter plot, we see that the 12 most populous counties all voted for Obama, and that most of the counties with small populations voted for McCain. To generate a scatter plot, we plot the data as points by setting the marker and line style keyword arguments of plt.plot. And of course, we label the axes. So, we have exposed another graphical EDA technique, scatter plots. We would like to have a summary statistic to go along with the information we have just gleaned from the scatter plot. We want a number that summarizes how Obama's vote share varies with the total vote count. One such statistic is the covariance. To understand where it comes from, let's annotate the scatter plot with the means of the two quantities we are interested in. Now, let's look at this data point from Lucas County, Ohio. This data point differs from the mean vote share for Obama and the mean total votes. We can compute these differences for each data point. The covariance is the mean of the product of these differences. If x and y both tend to be above or both below their respective means together, as they are in this data set, then the covariance is positive. This means that they are positively correlated. When x is high, so is y. When the county is populous, it has more votes for Obama. Conversely, if x is high while y is low, the covariance is negative, and the data are negatively correlated or anti-correlated, which is not the case for this data set. We can compute the covariance using built-in NumPy functions that you will use in the exercises. However, if we want to have a more generally applicable measure of how two variables depend on each other, we want it to be dimensionless, that is, to not have any units. So we can divide the covariance by the standard deviations of the x and y variables. This is called the Pearson correlation coefficient, usually denoted by the Greek letter rho. It is the comparison of the variability in the data due to codependence, the covariance, to the variability inherent in each variable independently, their standard deviations. Conveniently, it is dimensionless and ranges from -1 for complete anti-correlation to 1 for complete positive correlation. A value of 0 means that there is no correlation at all between the data, as is shown in the plot on the upper left. Data with intermediate values are shown on the other plots. As you can see, the Pearson correlation coefficient is a good metric for correlation between two variables. Now that you know what the Pearson correlation coefficient is and what it means, you can compute it in the exercises using Python. You will then have an added tool in your EDA Summary Statistics toolbox. Let's do it. Imagine you measured the petal lengths of 50 flowers of a certain species. Here is the ECDF from those measurements. From what you have learned, you can compute the mean of those 50 measurements, and I'll annotate it on the ECDF with a vertical line. That is useful, but there are millions of these flowers on the planet. Can you tell me the mean petal length of all of the flowers of that species? If I measure another 50 flowers, I get a similar but quantitatively different set of measurements. Can you tell me what value I would get for the mean petal length if I measured yet another 50 flowers? We just don't have the language to do that without probability. Probabilistic reasoning allows us to describe uncertainty. Though you can't tell me exactly what the mean of the next 50 petal lengths you measure will be, you could say that it is more probable to be close to what you got in the first 50 measurements than it is to be much greater. We can go ahead and repeat the measurements over and over again. We see from the vertical lines that we expect the mean to be somewhere between 4.5 and 5 centimeters. This is what probabilistic thinking is all about. Given a set of data, you describe probabilistically what you might expect if those data were acquired again, and again, and again, and again. This is the heart of statistical inference. It is the process by which we go from measured data to probabilistic conclusions about what we might expect if we collected the same data again. Your data speak in the language of probability. Let's do a few exercises exploring these ideas, and then we'll come back and learn how to start speaking this probabilistic language. In practice, we're going to think probabilistically using hacker statistics. You had an introduction to hacker statistics in previous DataCamp courses, and in this course we will greatly extend your expertise. The basic idea is that instead of literally repeating the data acquisition over and over again, we can simulate those repeated measurements using Python. For our first simulation, we will take a cue from our forebears. The concepts of probability originated from studies of games of chance by Pascal and others in the 17th century. So, we will simulate coin flips. Specifically, we will simulate the outcome of 4 successive coin flips. Our goal is to compute the probability that we will get 4 heads out of 4 flips. NumPy's random module, a suite of functions based on pseudo-random number generation, will be our main engine for doing this. To simulate a coin flip, we use the function np.random.random, which draws a number between 0 and 1, such that all numbers in this interval are equally likely to occur. If the number we draw is less than 0.5, which has a 50% chance of happening, we say we got heads, and we get tails otherwise. This type of experiment, where the result is either true, heads, or false, tails, is referred to as a Bernoulli trial, and we will work with these more as we go through the course. The pseudo-random number generator works by starting with an integer, called a seed, and then generates random numbers in succession. The same seed gives the same sequence of random numbers, hence the name pseudo-random number generation. So if you want to have reproducible code, it is a good idea to seed the random number generator using the np.random.seed function. Now to do our coin flips, we import NumPy, seed the random number generator, and then draw 4 random numbers. Conveniently, we can specify how many random numbers we want with the size keyword argument. The first number we get is less than 1/2, so it is a heads. But the remaining 3 are all tails. We can show that explicitly using the less than operation, which gives us an array with the Boolean value true for heads and false for tails. We can compute the number of heads by summing the array of Booleans, because in numerical contexts, Python treats true as 1 and false as 0. We want to know the probability of getting 4 heads if we were to repeat the 4 flips over and over and over again. We can do this with a for loop. We first initialize the count to 0. We then do 10,000 repeats of the 4 flip trials. If a given trial had 4 heads, we increase the count. So what is the probability of getting all 4 heads? It's the number of times we got all heads divided by the total number of trials we did. The result is about 0.06. Pascal and his friends did not have computers and worked out problems like this with pen and paper. While this particular problem is tractable, pen and paper statistics can get hard fast. With hacker statistics, you pretty much do the same procedure every time. You figure out how to simulate your data, simulate it many, many times, and then compute the fraction of trials that had the outcome you're interested in. Now let's use hacker statistics to simulate some more data.